Lesson 15 is about segments and triangles, and 15.1 discusses medians. You may have heard the word median in a math class before, like when you learned about mean, median, and mode. It's a different type of median, but it does kind of have to do with finding the middle of something. So yeah, not related, but similar meaning, kind of. Now we're just dealing with triangles. So median of a triangle is a line segment that connects a vertex of the triangle to the midpoint of the side that is opposite that vertex. So the vertex is like the corners of the triangle. So there's three vertices. So a triangle has three medians because of its three vertices. So each vertex, sorry, gets a median. So since there's three vertices, there are three medians. Okay, so looking at the graphic on the right, you can see there's a vertex at A. The median like goes straight directly out of it and it goes to the side that is opposite of A, and it creates or it connects to a midpoint of that side. The reason that is important is because basically it cuts that side in half. So you can see like on the left side of the median, there's 1, 2, 3 tick marks, and then on the right side, there's 1, 2, 3 also. That's always true. So every time you have a median, it'll extend from the vertex, say C, to the opposite side and then cut that opposite side into two congruent halves. And then the last one from vertex B goes over to the opposite side, cuts that opposite side into two congruent halves. Okay, so going back to over here, segment AD, segment BE, segment CF are all the three medians of triangle ABC. So AD, that was the first one, and then BE, that was this one right here, and then CF was that third one. Okay, moving down to where it says concurrent lines. So concurrent lines are three or more lines that intersect in a single point. They don't necessarily have to be in a triangle, but they're just three or more lines that intersect at a single point. So if I have like a line right here, a line right here, a line right here, those are considered concurrent points. And then the point where they intersect is the point of concurrency. So that point of concurrency on this example would be right here. On our triangle, it would be in the center. Okay, moving down to the next line just kind of adds to what I just said. Jumped the gun a little bit, but in a triangle, the point of concurrency is called the centroid of the triangle. So it's not really like a true like center because it's not like a circle, but it's a fancy word for center, kind of. It's centroid. So centroid of the triangle is that point where the three medians cross each other. Okay, moving down to our new theorem is right here, another one to add to the list. This one doesn't really have a name, I don't think. At least I couldn't find the name, so we're just going to call it the new theorem. It's the medians of a triangle are concurrent. So you can see that in the graphic. There was the three medians, AD, BE, and then CF, and they created three like line segments that all intersected in a single point, so they're all concurrent. Okay, we're going to move on to the proof. So the given and what we're trying to prove is in the upper right corner now. So given segment AD is a median, so right here. And then we're also given that segment AC is congruent to segment AB. So segment AC is congruent to AB. I'm just going to go ahead and add the tick marks to the graphic to remind us. And then we want to prove that angle ACD is congruent to angle ABD. So ACD is ACD, so it's this angle. And then angle ABD is ABD, so that's this angle. So we're trying to prove that like the angle on the like bottom left and the angle on the bottom right are congruent to each other. Okay, so remember always stating like what's given to us first. It doesn't matter which part you state first. I'm just going to put the first line, segment AD is a median. And our reason is that it was given to us. And then the second piece of information that was given was this second line, segment AC is congruent to segment AB. So segment AC is congruent to segment AB, and then if that wasn't like drawn on your picture yet, I would just add the two tick marks so you can like kind of see it on the picture that we know that those two are congruent rather than like having to like look back and forth and find the segment each time. And then that's all of our given information. So state that that's given, and then we're ready to move on to step 3. So for 3, if we know that, let's say, so we know that segment AD is a median, then we also know that point D is a midpoint, because that's what a median does, is it cuts something, or it goes like from the vertex to the midpoint of the other side or of the opposite side. So for 3, we would say point D is a midpoint. And the reason that we know that it's a midpoint is because we know that, AD is a median that was given to us. And what does a median do? It cuts the opposite side into two congruent halves. It connects to the midpoint. So I'm just going to go back up here really quick. So it says it connects a vertex to the midpoint of the opposite, or of the side that's opposite the vertex. So we went from the vertex to the midpoint D. So because we were able to like say that it was a midpoint because we knew that AD is a median, we would like justify this by saying definition of a median, because that's why we were able to establish that D was a midpoint. And then now that we know that D is a midpoint, we can go ahead and say that, CD is congruent to DB, that those two sides are equal, or not equal, but congruent to each other, because that's what a midpoint does. So we can say that segment CD, is congruent to segment DB, because we know that D is a midpoint, and a midpoint cuts a segment into two congruent halves. So our justification would be definition of a midpoint. And then for the next step, we're kind of getting to like, we have a couple different like pairs of corresponding parts that are congruent. So we're ultimately trying to show, remember that like this angle and this angle are congruent, because we don't really have any technically any information. I know that this looks like a right angle, but we don't know that for sure. Because we don't technically have any information about the angles, we're probably going to have to do it by showing that the triangles in general are congruent. And then if we can show that the triangles in general are congruent, then we can say all the angles are congruent, all the corresponding angles. So we have to take a step back and look, okay, what do we know so far? So we have like these two pairs of corresponding sides that are congruent. We have these two pairs of corresponding sides that are congruent. And then this is a shared side, so that's definitely congruent, but we just have to state that it is. So we would say segment AD is congruent to segment AD. And that's that one where it's like, anything is congruent to itself. That's called the reflexive property of congruence. So reflexive property of congruence. And then once we show that, we say, okay, segment AD is congruent to itself. So we've like figured out that all 3 pairs of corresponding sides of each triangle are congruent to each other. So if we have 3 sets of like corresponding parts, that's typically enough. There's a few cases where it's not, but in this case, we have 3 different pairs of sides. So we do have a congruence postulate for that. So we can stop and say that the triangles are congruent. We would say triangle A CD is congruent to triangle ABD. So I forgot the triangle on that one. And then remember that when you're like writing the triangles like ACD and ABD, you need to pair up like the letters that correspond with each other. So what I mean by that is like, this is angle AA, those two are corresponding, and then C and B, those two are corresponding, and then D and D, like each of those sides is also corresponding. And then we were able to say that because we showed that there's three pairs of corresponding sides. So we have a side, a side, a side. So that is the side, side, side congruence postulate, and we shorten it by S, S, S. And that stands for side, 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 and then congruence postulate. And then now that we've said that, oops, I'm trying to make that a little bit smaller. Now that we've said that the two triangles are congruent, that's enough information to say that all of the corresponding parts are congruent. So we can now say like what we're trying to prove, which was angle ACD is congruent to angle ABD. So angle ACD is congruent to angle ABD. And remember when like we're writing these angles, the vertex is in the middle. So this is like A, C, D. That would be this one right here with the C in the middle. And then A, B, D would be, has the A in the, or sorry, the B in the middle. So it'd be A, B, D, the angle right here. And then our like justification for this, you can shorten it if you want, but it's, so if we've shown that two angles are congruent, or two triangles are congruent, that means that all of their corresponding parts are also congruent. So since we were able to accomplish 6, we can go ahead and say that any corresponding part that we need to is congruent out of these two triangles. So our reason would be corresponding parts of congruent triangles are congruent. So corresponding parts of congruent triangles are congruent, meaning every single set of corresponding parts are going to be congruent. And then that's the last part of 15.1, so we're going to move on to 15.2. 15.2 is about midsegments. So starting up at the top, a midsegment of a triangle is a line segment that connects the midpoints of two sides of the triangle. So if we use the graphic on the right, you can see, okay, there's a midpoint at F because it cuts this side in half into two congruent halves. There's a midpoint at E, it cuts AC into two congruent halves. And then if I connect those two midpoints, that's my midsegment. So FE would be a midsegment, or EF, depending on the way that you write it. And you can see that there's a total of 3 midsegments. It's basically like that red triangle within the blue triangle is our 3 different midsegments. So every single triangle has 3 midsegments on this graphic. They're EF, and then DF, and then DE. So because there's 3 midpoints, like one for each side, there ends up being like 3 combinations of like mid segments that you can create. Okay, moving down to the new theorem. This one has a name. So triangle midsegment theorem. If a segment is a midsegment of a triangle, then it's parallel to the third side and half the length of the third side. So what that means is, so let's say I have a mid-segment right here at FE, And that's the mid-segment because it connects the two midpoints of AB and AC. So when it says the third side, like right here it says third side, and then right here it says third side, it's referring to the side that the midsegment does not connect. So in this case, it's referring to BC. So we're focusing on FE and BC, the two highlighted in purple. And then if we just read through the theorem one more time, if a segment is a midsegment of a triangle, then it's parallel to the third side and half the length of the third side. So that means that FE and BC are parallel, and then FE is also half the length of BC, or BC is double FE. Okay, moving down to the proof. So what we're trying to prove is on the right side and what we're given as well. So we're given that segment BF is congruent to segment FA. I'm going to put that on the graphic also. So BF is congruent to FA, and then also BD is congruent to DC. So BD is congruent to DC. We don't really know anything about the relationship between BF and BD or anything, so we want to use a different set of tick marks, like 2 versus 1. And then we're trying to prove that segment FD is congruent to segment AC. So we're trying to show that this side, oh sorry, not congruent, my bad, I don't know why I said congruent, but parallel. We're trying to show that segment FD is parallel to segment AC. So FD, that one in pink, and then AC, the one that just got drawn over in pink as well. We want to prove that those two are parallel. Okay, so I'm actually going to leave that there because I think it's a nice visual. Okay, so for our proofs, remember to start with what you're given. So I'm just going to put them together. So BF, or segment BF is congruent to segment FA, segment BD is congruent to segment DC. So segment BF is congruent to segment FA, and then also the segment BD is congruent to segment DC. And then of course that was given to us, so that's our reason, is that it was given. And then next for number 2, so because we know that those kind of pairs of sides are congruent, it's safe to say that the points that separate them are midpoints. So we know that BF and FA, those are the same length. So that means that this point in the middle is a midpoint. So we can say F is the midpoint of segment BA. And then we know the same for segment BC as well. So if BD is the same length or is congruent to segment DC, that means that the point that separates them, point D, is exactly in the middle. It's the midpoint of that entire segment of BC. So we would say D, and if you just want to write quotes under, I'm going to rewrite the full thing, but D is the midpoint of segment BC. And the reason for that, or the justification, is, that's what a midpoint is. It cuts a segment into two congruent parts, which we have a segment. We have BC that's cut into two congruent parts. We also have segment BA that's cut into two congruent parts. So we can say definition of a midpoint. We knew it was a midpoint because it cut its segment into two congruent halves. Okay, and then for the next part, I want to go back up really quick to just like what the definition of a mid-segment was. That was the word that we learned with 15.2. So that's just at the very, very top. The mid-segment of a triangle is a line segment that connects the midpoints of two sides of a triangle. So we've gone ahead and we've stated that, F and D, those are midpoints. So now we can say, okay, segment FD is a mid-segment. Before we could do that, we had to state that F and D were midpoints, but now that those are stated, we can say that FD is a mid-segment because that's what a mid-segment is. It's a line segment that connects the midpoints of two sides of a triangle. Okay, so for number 3, we would say FD is the mid-segment, or is the mid-segment. You could say is A, I guess, is a mid-segment of triangle ABC. So segment FD is A, or the mid-segment of triangle ABC. And we just kind of established that by going back and rereading the definition of a mid-segment. So that's what our reason is going to be, is definition of a mid-segment. Okay, and then before we go to 4, I just want to read through the triangle mid-segment theorem one more time. So remember, ultimately, we're trying to prove that segment, let me erase some of this, sorry. Segment FD, which is this one, is parallel to segment AC, which is this one. And we just learned a new theorem, so starting right here. If a segment is a mid-segment of a triangle, which this one is, so FD is a mid-segment of the triangle, then it's parallel to the third side. So parallel to the third side, this is the third side. It's like the side that the mid-segment does not connect. So we can use that theorem as justification to prove what we're trying to prove. So you would say FD, or segment FD, is parallel to segment AC. And then our reason would be the triangle mid-segment theorem, this one right here.